Ready for a deep dive into a world where numbers aren't just numbers, they're keys to unlocking the universe's secrets.
Sounds intriguing.
We're diving into 17 equations that change the world by Ian Stewart. And trust me, these equations are way more than just formulas on a chalkboard.
I'm guessing we're talking about the kind of equations that reveal the hidden architecture of everything around us.
Exactly. They're like blueprints to reality. And get this, they often do it with a simplicity that's almost poetic.
I'm all for finding poetry in unexpected places, especially in the world of math.
Well, get ready for a surprising amount of it, starting with a familiar face, at least from our high school geometry days. Pythagoras, you know, A plus B brighter than that East one.
Ah, yes, the Pythagorean theorem. It's practically a rite of passage for anyone who's ever grappled with triangles.
Right, but here's the thing. It's way more than just triangles. It's a fundamental statement about spatial relationships, about distances on a plane.
And those relationships, those distances, they're everywhere. Did you know that ancient civilizations might have used the Pythagorean theorem to measure the Earth's circumference?
Wait, really? That's like using the humble triangle to wrap your head around the entire planet.
It just goes to show you the power of a simple equation to unlock some pretty mind-blowing concepts. And speaking of unlocking things, let's talk about another equation that, while maybe not as famous as Pythagoras, had an absolutely massive impact on scientific progress: logarithms.
Okay, I'll admit, logarithms always seemed a bit like mathematical black magic to me. Something about turning multiplication into addition.
It does sound a bit like alchemy, doesn't it? But here's the thing. Before calculators existed, imagine astronomers dealing with these incredibly long, tedious calculations, multiplying huge numbers by hand.
I can only imagine the headaches and ink stains.
Logarithms came along and basically said, hold my abacus. They provided a way to simplify those calculations, saving countless hours and reducing errors.
It's like they found a shortcut through a mathematical jungle. No wonder mathematicians were so excited about them.
Oh, absolutely. There's this fantastic letter from mathematician Henry Briggs to James Ussher, where he describes his excitement upon discovering logarithms. He writes, "Napper, Lord of Markenston, hath set my head and hands a work with his new and admirable logarithms."
Set my head and hands at work. It's a game changer when a mathematician gets that fired up.
Yeah.
And speaking of game changers, calculus comes to mind. It's all about understanding how things change, right?
Exactly. It's the mathematics of motion, of rates of change, of understanding how one quantity varies in relation to another.
So when Galileo was figuring out the parabolic path of a cannonball, was he already tapping into calculus concepts, even if it wasn't fully formalized yet?
He was. It's fascinating how great minds often converge on similar ideas. Calculus, in its essence, was waiting to be discovered.
Speaking of converging minds and waiting to be discovered, there's that whole saga with Newton and Leibniz both developing calculus independently.
Ah, yes, the infamous calculus controversy.
Didn't that cause quite a stir in the mathematical community?
It did indeed, and you'd think such a groundbreaking discovery would be cause for celebration, but instead,
It became a bit of a mathematical turf war.
you could say that. While we won't get bogged down in who gets the credit here, the controversy actually ended up hindering the progress of English mathematics for a significant amount of time.
Really? How so?
While the rest of Europe embraced Leibniz's notation and approach, English mathematicians clung to Newton's methods.
It seems even brilliant minds can get stuck in their ways.
It's a reminder that the pursuit of knowledge, while noble, isn't always smooth sailing.
But despite all the drama, calculus still stands as this incredibly powerful tool for understanding the universe, right?
Absolutely. It's how we describe everything from the motion of planets to the behavior of fluids, even the expansion of the universe itself.
It's amazing how an equation can capture the essence of something so vast. And speaking of vast things and the laws that govern them, that brings us to Newton's law of gravity.
Ah, yes. The equation that literally changed how we view our place in the cosmos.
It's this elegant little equation based on the inverse square law that explained why planets move in those elliptical orbits, which, if I remember correctly, was a bit of a head-scratcher for astronomers before Newton came along.
It was a major piece of the cosmic puzzle. Before Newton, the heavens were this mysterious realm governed by unseen forces.
And Newton basically said, "Hold my falling apple."
Pretty much. And like with calculus, there was a bit of debate about who really deserved credit for the underlying principles, this time between Newton and Robert Hooke.
It seems like those scientific revolutions were often accompanied by a bit of ego clashing as well.
Yeah.
But let's not get sidetracked by the drama. The important thing is that Newton's law of gravity works, right? I mean, it accurately describes how planets move.
It does, well, for the most part. It works beautifully when you're dealing with two bodies, like the Earth and the Sun, but throw in a third celestial object, say, the Moon, and things get a bit more complicated.
Ah, so our elegant law has its limits.
Even the most fundamental laws of physics have their boundaries. This is the famous three-body problem. Figuring out the precise motions of three objects all interacting gravitationally is surprisingly complex, even with Newton's equations.
It's a good reminder that the universe loves to keep things interesting. But even without solving the three-body problem perfectly, understanding these gravitational interactions has still led to some amazing advancements, right?
Oh, absolutely. Think about Lagrange points, those special spots in space where the gravitational forces of multiple bodies create a sort of equilibrium.
Right, I've heard of those. Aren't they like gravitational sweet spots that we use for things like positioning space telescopes?
Exactly. It's a great example of how even an incomplete understanding of a complex system can still lead to incredible practical applications.
It's like we're catching glimpses of the universe's rulebook, even if we don't have all the pages yet. But speaking of rules, things get really interesting when math takes us into territory that seems to defy logic altogether.
And what could be more logic-defying than trying to find the square root of a negative number?
You know, it's funny how something that seems like a mathematical dead end can actually open up whole new avenues of exploration.
It's like stumbling upon a secret passageway hidden within the structure of math itself.
And sometimes those passageways lead to some surprisingly practical destinations.
Exactly. The square root of n of 1, for example. It gave rise to complex numbers, which might sound like something out of a science fiction novel, but are actually essential tools in fields like electrical engineering, signal processing, even quantum mechanics.
It's like those imaginary numbers ended up having a very real impact on our understanding of the universe.
It's a beautiful example of how abstract mathematical concepts can end up having tangible effects on our lives.
Speaking of abstract concepts, let's talk about a branch of math that often gets filed under mind-bendingly abstract topology.
Ah, topology, the study of shapes and spaces, but with a twist.
A twist.
Well, it's less about precise measurements and angles and more about the fundamental properties of a shape that remain constant even when you stretch it, twist it, or deform it.
So it's about the essence of a shape, not its rigid form. What kind of properties are we talking about?
Think about a donut and a coffee mug.
Okay, delicious combination, but I don't see the connection to topology.
To topologists, those two objects are surprisingly similar. They both have one hole, and that property, the number of holes, remains constant even if you stretch the donut into a pretzel shape or mold the coffee mug into something unrecognizable.
So topology is about those underlying connections, those shared properties that might not be immediately obvious.
Exactly, and it all goes back to a deceptively simple equation, Euler's formula for polyhedra. It relates the number of faces, edges, and vertices of a polyhedron, and it turns out this simple relationship hints at some pretty deep truths about shapes and spaces.
Truths that then gave rise to this whole new field of mathematics dedicated to understanding the very fabric of space itself. It's mind-boggling.
It really is. It just goes to show you that even the most abstract mathematical explorations can end up revealing something profound about the universe we live in. And speaking of profound, let's bring things back down to earth, so to speak, with an equation that's a bit more familiar, at least in a visual sense. The bell curve, also known as the normal distribution.
Right, the bell curve. That's all about probability and statistics, isn't it?
It is. It's a visual representation of how data tends to cluster around an average value, with fewer data points the further you move from that center.
So it's about understanding the likelihood of things, how often certain outcomes occur within a range of possibilities.
Precisely. And the story of how it emerged is fascinating. It has roots in everything from gambling to astronomy.
Gambling and astronomy, that's quite a range. What do those two fields have in common?
It's all about patterns and predictions. Gamblers were trying to understand the likelihood of certain outcomes in games of chance, while astronomers were grappling with errors in their measurements of celestial bodies.
So the bell curve emerged as a way to make sense of randomness, to quantify the likelihood of different events.
Exactly. It's become an essential tool in countless fields, from finance to physics to social science.
Though I imagine applying it to human characteristics like heights or intelligence can be a bit of a slippery slope, right?
You're right to be cautious. The bell curve itself is a neutral mathematical tool, but how it's used and interpreted, especially when it comes to human traits, is a whole other can of worms.
It's a good reminder that even the most elegant equation can be misused.
It's a reminder to always be mindful of the context. But speaking of applications, let's shift gears from the statistical world to something a bit more melodic. The wave equation, which describes the very essence of sound.
Okay, now we're talking. I always love the idea that music has this deep connection to mathematics.
It's true. The wave equation describes how vibrations travel through a medium, whether it's air, water, or even a violin string.
So when we hear a musical note, we're essentially experiencing a mathematical equation in action. That's a pretty cool way to think about it.
It is. The wave equation allows us to understand things like frequency, which determines the pitch of a sound, and amplitude, which relates to its loudness. These properties that we perceive as musical qualities can be precisely described and manipulated using mathematical equations.
It's like math is the secret language of music.
It's a language that's spoken throughout the universe in ways we're still just beginning to understand. And speaking of languages, there's one equation that's notoriously difficult to decipher, even for the most skilled mathematicians. The Navier-Stokes equation, which governs fluid flow.
I've heard of that one. It's supposed to be a real bear to work with.
It's true. The Navier-Stokes equation describes the motion of fluids, from the air we breathe to the currents in the ocean. But despite its complexity, or perhaps because of it, it's one of the most important equations in physics and engineering.
So if it's so challenging, how do we actually use it?
That's where the power of computers comes in. While finding exact solutions to the Navier-Stokes equation for complex scenarios is often impossible, we can use powerful computers to generate approximate solutions. This has led to the field of computational fluid dynamics, which has revolutionized things like aircraft design, weather forecasting, even medical research.
So from designing more aerodynamic cars to predicting hurricane paths, it all comes back to this one incredibly complex equation.
It's a testament to the power of mathematical modeling, even when dealing with incredibly complex systems.
And sometimes those complex systems lead us to equations that completely upend our understanding of reality itself. I'm thinking, of course, about Einstein's famous EMC, which fundamentally changed how we think about energy, mass, and the very fabric of the cosmos.
Ah, yes. EMCF4, it's more than just an equation, it's an icon.
It's practically synonymous with scientific genius. But beyond its fame, what's really so revolutionary about it?
It's the profound statement it makes about the relationship between energy and mass. These two fundamental quantities, long thought to be separate entities, are actually two sides of the same coin.
So mass can be converted into energy, and energy into mass. It's like the universe is harboring this incredible potential, just waiting to be unleashed.
And unleashing that potential, even just understanding it theoretically, has had mind-blowing consequences. EMCO didn't just change our understanding of physics. It paved the way for some of the most significant technological advancements of the 20th century.
It's both awe-inspiring and a little bit terrifying at the same time. But before we spiral into an existential crisis about the nature of reality, let's talk about another one of Einstein's brain-bending contributions. The theory of relativity. It really is a mind-bending concept, the idea that time itself isn't this constant, unwavering thing we experience it as, but is actually flexible, relative.
It challenges our everyday intuition, but think about it this way. We're used to thinking about speed limits in terms of miles per hour or kilometers per hour.
Right, distance over time.
Exactly. But what if the time part of that equation isn't constant? What if time itself is variable, influenced by things like speed and gravity? That's what Einstein's theory of relativity throws into the mix.
So the closer I get to the speed of light, the slower time moves for me relative to someone standing still.
Yeah.
It's like something out of a science fiction movie, but it's real.
It's stranger than fiction. And it's not just about speed. Massive objects like planets and stars, they actually warp the fabric of space-time itself. Imagine a bowling ball placed on a trampoline.
I can picture that.
It creates a dip, a curvature.
Yeah, right.
Well, massive objects do something similar to space-time. They warp it, and that warping is what we experience as gravity.
Okay, that's kind of blowing my mind right now.
Yeah.
So gravity isn't just a force, it's a consequence of curved space-time. It's like the universe is playing a cosmic game of four-dimensional billiards.
And we're just starting to understand the rules of the game. But speaking of mind-bending concepts, we can't forget about quantum mechanics and the equation that's launched 1,000 memes, the Schrödinger equation.
Ah, yes, the equation that brought us the infamous thought experiment of Schrödinger's cat, simultaneously both alive and dead. It's the kind of thing that makes you wonder if physicists are secretly just messing with us.
It's definitely one of those concepts that captures the imagination, even if it leads to a lot of head scratching along the way. But at its core, it's trying to illustrate a very real phenomenon in the quantum world: superposition.
Superposition, meaning something can exist in multiple states at the same time. That's where my brain starts to short circuit a bit.
I don't blame you. It's not exactly intuitive. Imagine flipping a coin.
Okay, got it.
Until it lands, it's both heads and tails simultaneously, right?
In a way, yeah.
Well, in the quantum world, particles can exist in this kind of blurry state of superposition, holding multiple possibilities at once until we observe them. That's the basic idea behind Schrödinger's cat.
So the cat in the box is both alive and dead until we open the box and force the universe to choose.
It's a thought experiment designed to highlight the strangeness of quantum mechanics. Of course, in reality, cats don't tend to behave this way, and that's an important point.
So there's a difference between the quantum world and our everyday experience.
Right. Quantum mechanics governs the realm of the very small, the subatomic world. But as things get bigger, the rules of classical physics, the ones we're used to, tend to take over.
So the universe has different sets of rules depending on the scale you're looking at. It makes you wonder what other hidden layers might be out there just waiting for us to discover them. But speaking of discoveries, no deep dive into equations would be complete without mentioning information theory, right?
Absolutely. And no discussion of information theory is complete without mentioning Claude Shannon and his groundbreaking work.
Because he basically found a way to quantify information itself, to measure it mathematically.
Exactly. Shannon developed equations that describe information in terms of its probability and uncertainty, kind of like how the bell curve describes the distribution of data.
And this has had huge implications, hasn't it? I mean, it's the foundation of our digital age.
It's hard to overstate the impact of Shannon's work. From designing more efficient communication systems to developing error-correcting codes that ensure data reliability in our digital devices, it all goes back to understanding information in this mathematical sense.
It's like he gave us the tools to tame the very essence of information itself. And speaking of taming things that seem inherently untamable, the logistic map comes to mind.
Ah, yes, a deceptively simple equation with a knack for chaos.
It's like the mathematical equivalent of a butterfly flapping its wings and causing a hurricane on the other side of the world.
Exactly. It's a prime example of chaos theory in action, where tiny changes in initial conditions can lead to vastly different outcomes, making long-term prediction incredibly difficult.
It's a good reminder that even with all our fancy equations and models, the universe always has a few surprises up its sleeve.
A bit of humility is always a good thing when it comes to understanding the complexities of the universe. And that brings us to our final equation for this deep dive, an equation that's been both praised and vilified: the Black-Scholes equation.
It's a bit of a controversial one, isn't it? I've heard it described as both a groundbreaking tool and a recipe for financial disaster.
It's a great example of how even the most elegant mathematical models can have unintended consequences, especially when they're applied to complex systems like financial markets.
So what does the Black-Scholes equation actually do?
It's used to price financial derivative, things like options and futures, which are basically contracts that derive their value from an underlying asset.
Sounds complicated.
It is, but the key point is that the Black-Scholes equation, while powerful, relies on a number of assumptions about market behavior. When those assumptions hold true, the equation works well, but when they don't.
Things can go haywire pretty quickly.
Exactly, and that's a risk with any model, whether it's in finance, physics, or meteorology.
We're always simplifying, making assumptions, trying to capture the essence of something incredibly complex in a neat little equation. But reality has a way of throwing curveballs.
It's a humbling reminder that while our mathematical models can offer incredible insights, they're always just approximations of a much messier and often unpredictable reality.
It's been an incredible journey exploring these 17 equations that changed the world. It's amazing to think about the profound impact these seemingly abstract mathematical expressions have had on our understanding of the universe and our place in it. What's the key takeaway you hope our listeners will carry with them from our deep dive today?
I hope they'll come away with a sense of wonder, a sense of awe at the power of human curiosity and ingenuity to unravel the mysteries of the universe, one equation at a time.
Beautifully said. And to our listeners, keep exploring, keep questioning, and never lose that sense of wonder. The universe is full of fascinating equations just waiting to be discovered.